Thanks everyone for getting up a little bit earlier to accommodate our speaker who's from the UK today. I'd like to welcome Professor Stefano Pirandola from the University of York, who is also now the CEO of another quantum startup, nodeQ, who'll be talking to us today about quantum communications over the quantum internet. So Stefano, thanks a lot for staying up late.
Thank you very much, Simon, for this opportunity. And yes, let me share. Right. So this is yeah. So can you see this is actually this is actually online. So 8th of December UK, 9th of December in Sydney. Talking about quantum communications over the quantum internet. So this is so you mentioned this company, my startup that I've just founded this year, and this is about quantum networking. So we're developing software for quantum networks. Okay, so let us start with this talk. I mean, I am giving very I'm not technical because of course it's late here, it's early there, so I thought, okay, let's try not to give too many technical details. So I will keep this on a quite say a high level, notional level. Okay. So we start with this first part, it's quite general, and then I will move into more well, slightly more technical details, but not so much. Now we have this fantastic quantum ecosystem which is evolving now, and we know that you have quantum computing, quantum communication, quantum sensing. These are the three main areas that have been developing quite fast recently. And quantum internet, well, the quantum internet is a kind of interconnection now between all these areas. Okay, so in the quantum internet you have quantum computing device, you have quantum communication between this device, you have quantum security, which is an important part of quantum communication. But you also have quantum sensing, so you can put the sensors in a network, in a quantum network, to improve things like path recognition. So you have all these areas which are somehow they come together in a quantum internet. Okay, so let's talk about at the beginning how this ecosystem, our quantum internet, can be is actually developing. Okay, and how can I see this coming? So we have clearly increasing layers of complexity, if you want. And one thing that I put at the very basis is security. Okay, and so we have a level 0 and a level 1. So level 0, I put post-quantum crypto. This may be debatable for some people, because okay, post-quantum crypto is kind of a classical software solution, but yet this is a field that is clearly accounting for quantum computers, so is clearly well a reaction, a feedback to this to the presence, to the future presence. It is part of a secure quantum network at the end. Even though it is a classical purely software solution. We have also then a next step, which is a QKD, okay? So quantum key distribution. And clearly this is a now higher level because it also involves the development of dedicated hardware. Even though, in some cases, this hardware is pretty off-the-shelf telecom components. Right, and yeah, then we have of course, the talk I will talk about is level 0, level 1 actually. But let me go on. And to see more or less all the scenario. So we have also the classical quantum cloud. So we have these examples today somehow developed. So this is actually this is basically quantum processors that are connected with classical links. Okay, so quantum processors on the cloud that they can be used by people just by connecting via the classical internet interface. Then we have the next steps, which are becoming more and more difficult. So the development of repeaters. And here I have to tell you, I mean, this type of repeaters I'm talking about here are in particular entanglement distribution and repeaters. So devices that are able to distill entanglement, so they need to use more likely quantum memories. So the most advanced form of quantum repeaters. And clearly also interfaces. So we need to develop a very good frequency converters, for instance, between microwave photons and optical photons, so to interface, for instance, superconducting qubits and optical qubits. And finally, clearly, we have the quantum cloud. So it's the fully quantum scenario where you have quantum computers that now are connected using quantum links. So you have quantum states actually teleported from one quantum computer to another. And so that it would be basically the last step. We can implement many protocols at this level. You may have a fault-tolerant quantum computing. So that is actually the maximum level achievable. Now, all of this is based on a hybrid structure. Okay? So we don't have a winning technology. We have different things. For quantum communication, photons, quantum processing, there are many different solutions, different technologies. Quantum storage as well may be done with different types of technologies and so on. So basically, we have a hybrid structure, which we have to take into account when we consider this this ecosystem. So different technology, they need to communicate. We need to build interface. We need to optimize interface. We need to create also the software which organize all this, optimize all this architecture. Okay, so let's talk about security. Okay, so we have security post-quantum, crypto, and QKD. And as you see here, so that's an increasing level of security, but also in terms of cost, clearly. Post-quantum crypto is a solution. So we have some candidates that are currently being evaluated by NIST. And this is actually taken from Wikipedia. I think, yes, I should have acknowledged Wikipedia, sorry. And here we have like the three types of post-quantum solution that are currently considered. Now, security with QKD is stronger because it's not based on computational complexity, if you want. It's based on information theoretic security that and also clearly, I mean, the laws of quantum physics. Okay, so as you know, QKD is about distributing keys between two remote users. Clearly, you also have like other applications in quantum cryptography, like quantum digital signatures and quantum random number generators and so on. But QKD in particular is about key distribution, and we have a plethora of protocols. I'm touching bases with some of this. And so we are here in security with QKD. And here you see the scenario is, if you zoom on this, you see that there are other levels, clearly. We have the standard QKD, so we want to have a security with respect to the attacks against the channels, so the communication channels. And here we have several levels of security, individual, coherent, composable security, and so on. And then we have like an extra step, so the measurement device independent QKD, so that's basically besides the security, of the channel. Also, you have a security with respect to the detection setup, and then device independent, where you start basically using heavily using entanglement. So you have even higher level of security because of the monogamy of entanglement and its wonderful properties. Now the problem is that when you see it here, this arrow, so this is clearly increasing the security from bottom to top, but also is increasing the cost clearly of the technology, and also is decreasing the rate. So that's an important point. So this upper level is very has a very low rate. It's basically not a near-term solution. Well, these are the two levels are clearly implementable today, and I mean in the very next, in the very near term. Okay, so just to tell you that so we are specifically interested in quantum key distribution clearly in this talk. So what is an ideal scheme for security, for quantum security? Okay, so you want the highest possible security, information theoretic, so that's why we talk about quantum key distribution. You want to have high rate, especially in short range situations, so like, I don't know, local area networks, so like, I mean, a local Ethernet or a local wireless. You want robustness to long distances. So you want to go beyond your building and your city. So you want to connect far away. You clearly want both wired and wired capabilities. So you want wireless, potentially Wi-Fi, better than Li-Fi. So you, probably with microwave instead of optical. That's quite difficult, clearly. You want end-to-end capabilities. So you want the possibility to be robust with respect to untrusted and also reliable relays, nodes, which are in the middle in the network. You want to be scalable to many users using the network simultaneously. You want an easy integration with the classical infrastructure. You want reasonable cost. So you want a lot of stuff. And clearly, this system does not exist, will never exist. Okay. And so the point here is that, okay, an ideal system for quantum cryptography, quantum key distribution clearly is not possible. We need to find compromises. So what does it mean to find compromises in terms of these features? Is that basically you want to, the approach is basically you want to optimize some features given certain requirements. So for instance, what you can do, you can optimize the rate. No, that's an example. You want to optimize the rate and the speed, which is very important. So you would like to have, I don't know, a local network which is working, well, I mean, reasonable well in terms of bits per second. But then, okay, that's that optimization of this particular aspect has to be done considering a certain level of security, I mean, a maximal range for the network, particular topology. I mean, what is the topology of the network? The number of users that they use the network. So it's a constrained optimization, which is a very difficult problem. And it has to be solved case by case. So there is not a unique solution. And it's basically a very complex scenario. Clearly here, I mean, current technology and next developments in technology, from this perspective, I mean, this is an area where expertise is very important, and I mean, people from academia should probably well be involved more and more because of the complexity of clear this problem in a network. So why is happening? What is happening? Okay, why is a constraint optimization? Well, because there are trade-offs. Okay, so there are different trade-offs considered. And when you optimize QKD, well, I mean, I just list 3 of them, which are, in my opinion, quite well known. Clearly, the rate versus security level. So I just said, I mean, I mentioned this, I mean, slide. So clearly, if you want to increase the security level, you decrease the rate. And I mean, you see this in the same, also in the formulas themselves. You fix like an epsilon security also. I mean, about epsilon security is affecting directly the rate that you can access with that epsilon security of the protocol. Now you have also a trade-off between the rate and security versus the number of users. So if you increase the number of users, also you have a problem in terms of rate and also security of the network. Probably the most famous and studied is the last one here in this list, which is the rate versus distance. And this is actually what we are talking about now. So this is a very important, is one of the fundamental now difference between classical and quantum communication. And it is studied a lot. And today, I mean, it's a very big, it's a very hot topic. Okay, so let's talk about this. And clearly, this is an important factor, is an important feature when you have to consider, well, I mean, building a network, building a quantum communication system, where you want to have a very good rate. I mean, you have to account for this trade-off. It is inevitable by the laws of quantum mechanics. Okay, so let's talk about now this, which is about basically the fundamental rate loss limit of quantum communications. And here I'm going to give you, well, a bit more of details. And so, but it's still, I mean, at the top, I mean, it's still a high level, okay? So you have, consider this point-to-point scenario. You have Alice and Bob, and they are connected by a communication channel, okay? So communication channel in this very basic, it's very basic description as an important parameter, which is the transmissivity, here denoted by eta. And what is this transmissivity? Is basically the fraction of photons, okay? So we are using the optical photons from wavelengths to Bob. That's the most typical scenario. So eta is the fraction of photons that survive. Okay, so it's the fraction of photons that survive from Alice to Bob. So what happens to the remaining part, which is 1 minus eta, this is basically lost to environment. Okay, because these are lost into the environment, that is inevitable. I mean, these photons are potentially, well, in a QKD scenario, these photons are potentially intercepted, okay, by an eavesdropper who can then, well, listen to the conversation, try to get the key, and so on. So typically, this is what's happening in an optical fiber. So of course, we have other effects. Okay, we also have thermal noise, excess noise. I mean, we have other forms. Of course, we have noise, not just loss, but loss is the most important. So what's happening in an optical fiber? So exactly this. I mean, if you take like an optical fiber with some length d, so we have distance d between Alice and Bob in kilometers, right? And then you have a loss rate, which is, this is a very standard, 0.2 decibel per kilometer. And sorry, I'm a bit, okay, so 0.2 decibel per kilometer. So this means that any kilometer of fiber, you are losing the equivalent of 0.2 decibel. And so what's happening is that you can relate together. So you have like the transmissivity, clearly simply connected to the distance, and the loss rate by the simple formula. So you have like a transmissivity of, okay, that's quite simple. Okay, so that is the typical scenario. Now you have this, so you have this fiber, you have this Alice and Bob, they want to do some protocol for quantum key distribution. You want to say, you want to calculate the maximum possible key rate, secret key rate, that they can achieve over this channel, okay? So suppose they can actually have unlimited resources, they can implement the best possible protocol. What is the number of secret bits per use of the channel that they can achieve? What is the maximum amount, the maximum number? So this is also called the secret key capacity, or sometimes, okay, also secret key agreement capacity of the channel. So we gave a first answer into this problem in 2009 when I was when I was at MIT, and so we found that yeah, okay, Alice and Bob, they can achieve that very simple amount. So if you know eta, the transmissivity of the channel, then you compute minus log 2, 1 minus eta, and then you get an achievable amount of bits, secret bits per use of the channel, okay? So I mean, I proved this by using a tool which is called reverse coherent information, which is, okay, a reverse type of the reverse type of the coherent formation introduced by Seth and others. Actually, was probably late 90s. Okay, so we do the reverse. I introduced the reverse version, but also found a protocol which was able to reach this quantity, is reverse query information. So that was basically the first result. Then it took actually, the second answer actually came in 2015, sorry, 2 years to publish this paper. I mean, my daughter was born in the middle, and it was quite a mess in my life. So it took like forever. But the actual result was from 2015, and we found, okay, look, this is also an upper bound. So this quantity here is not only achievable, okay, with a protocol, but also really the really maximum you can get. So there is no protocol that can exceed this rate. So this is an upper bound. So, and this was proven in this paper, okay, on publishing natural communications with my collaborators. And so what's happening when you have clearly, I mean, a lower bound and an upper bound that they match perfectly. So you're very lucky because you have exactly determined the capacity, really. So the cyclic capacity is exactly of the lossy channel is exactly this here. So given by this very simple formula. So this is very remarkable because it is very simple, yet very general. And it's actually also known as the plot bound from, I mean, me and my collaborator. Okay, so why this is important, clearly? Because it's a very general result applicable to many different scenarios in quantum communication. So, and so the important point is that actually when we proved this, we didn't prove this only for quantum key distribution. I mean, this actually holding for other tasks too. So it is not only the optimal rate. So it is not only the optimal rate for quantum key distribution. So it is not only the cyclic key capacity of the channel, but this quantity here is also the entanglement distribution capacity of the channel. So it's the maximum number of entanglement bits per use that you can distribute over the channel. And it's also the so-called two-way assisted the quantum capacity of the channel. So now the most advanced version of quantum capacity that you can define over this type of channel. And so it is the maximum number of qubits per use of the channel that you can send. So it's remarkable that also all these three capacities, they actually coincide, okay? So there are three capacity, they coincide all together into this simple formula. I think this basically, I think this is actually the best result of my life so far. And so it's important because, I mean, now we have this very simple formula, so very applicable. And this provides basically the ultimate performance of any quantum communication protocol over a lossy quantum channel in absence of repeaters. So be careful now, because here we have Alice and Bob, and we have a channel. So what does it mean? There's actually a somehow direct communication. Okay, so you don't have anything in the middle helping the communication. So we have a point-to-point, a direct channel between the two. Okay, so there are no repeaters. There is no third party in the middle. This is why also it's also called repeaterless bound. Okay, or well, repeaterless capacity. I mean, people have used different names. But I mean, repeaterless bound is very appropriate. And okay, so this also implies another thing, that from informational theoretical point of view, what is a quantum repeater now? So a quantum repeater, I mean, quantum repeater in quantum optics is typically connected with entanglement distillation, okay? So, and probably the use of quantum memory. So it's basically you connected with entanglement distribution, okay, in general speaking. Now, more generally, quantum repeater is basically can be seen as a relay, a third party, okay, which is able to help the quantum communication between both in such a way to beat basically this bound, okay? So whenever there's a third party in the middle, which is able to go beyond that value, so you are beating the repeaterless bound. So you are actually introducing something that effectively repeats, okay? So if you think about that, I mean, if you actually, if you look at, if you read a book, I mean, if you take a book on classical information theory, and then you find the relay channel, okay? So the relay channel is what is the relay channel? It's just the presence of a third party helping the communication between a sender and a receiver, okay? And the idea is that, I mean, from the point of view of quantum information theory, you can say the same, okay? So you have a third party which is able to help the communication in such a way to beat this repeaterless bound. Automatically, you have what I would call a quantum repeater, okay? Even though, I mean, this is not in the sense, the standard quantum optics sense. Okay, so let us plot this, and you see this is like a bob in distance. So let's say this fiber distance would be from 0 to 400 kilometers. And then we plot the cyclic key rate in terms of bit per use. Clearly, this become bits per second. Now, if you include a clock in the system, okay. So we are thinking about number of. So we are sending systems through the channel. Inserting a clock means that you are considering a number of systems generated per second, and then basically you have that you can transform this quantity here in bits per second. So it will become, with a clock, it will become the throughput of the channel. But again, let's try to be general. So we have this kind of scenario with this eta computed from this distance and the standard typical loss rate, and we have this decay, okay? And asymptotically, this is just 1.44 eta bits per use. Okay, so you cannot really beat this. So you go ahead, you see that actually standard QKD protocols are beyond this, okay? So you can see that, I mean, one photon ideal BB84 is that line, decoy, BB84 with decoy states optimally is this line, and these are actually ideal protocols for this, ideal rates for these protocols. The realistic rates are a bit different, but I mean, I want just to show that even if you boost, I mean, their performances, you cannot achieve that bound. Also, the VMDI, even though this is not a point-to-point protocol, was not really behaving well because it's way below. Now we have CP continuous variables, continuous variable QKD as the highest rate potentially, and the red line, the plot bound, is achieved by a specific continuous variable protocol, which, by the way, has to use quantum memories for Eisenbomb. So it's very complicated. But this line here are realistic continuous variable protocols based on queer states and heterodyne homodyne detection. They're pretty much the same performance, okay? I think this one plotted is with heterodyne detection. So what's this area then? These are all accessible with repeaters, okay? So if you want to go here, I don't know, you want to be at 300 kilometers and you want to have, I don't know, a rate in this region. So you can not do that with just a single fiber. You need to split the fiber. You need to introduce a repeater in the middle, okay? The point is that how much of this region is accessible, for instance, with one repeater. So now let's try to see now the next challenge. So we have this kind of limit for point-to-point. So what is now the limit for one repeater? What is the limit for two repeaters in terms of two repeaters in terms of maximum key rate? Okay, so we have also an answer to this question, and actually in this paper was also originally in 2016 the first version, then it was delayed a lot again because of family issues. But okay, so we have generally speaking, we may have like Alice and Bob with a number of repeaters in the middle, so R1 to Rm, so let's say M repeaters, and then we have M+1 segments of, for instance, fiber, okay? And the question is, okay, what is the maximum key rate achievable by Alice and Bob? So the answer given by this paper is pretty simple. I mean, proving the lower bound is trivial, clearly. I mean, proving that this is achievable is trivial. Proving that this is also an upper bound is absolutely non-trivial, is actually the main point of this paper. So, and the two bounds coincide, so you really get the capacity. And you can see that the modification is that now you need to account for the, I mean, it's pretty intuitive. You have to account for the minimum transmissivity in the here in the chain, okay? So the minimum transmissivity gives you the overall capacity of the chain. And that's, I mean, this is actually obvious also from, I mean, in terms of our classical knowledge, you know, in terms of widest path and shortest path, okay, classical information theory. So the bottleneck is given by the minimum transmissivity, okay, along the chain. Okay, now that's also not a pretty simple formula. So what's happening with the single repeater? So you have Alice and Bob, and suppose you have this fiber, the transmissivity eta. Now suppose that you split the fiber, so you cut the fiber in two. So when you cut the fiber in two, okay, if you don't use losses, clearly, I mean, you have two shorter fibers with square root eta transmissivity, each of them. And then you put a repeater in the middle. And clearly, I mean, in this situation here, you have that the best you can get is from the previous formula for the case equal, for just, I mean, one repeater, you have that specification of the formula, which is, as you can see, very simple. And again, I mean, the modification with respect to the plot bound is just that here you don't have, instead of eta, you have a square root of eta. And this clearly makes all the difference in terms of performance, because when you plot now the performance of this single repeater capacity, okay, you see that clearly the scaling is much better, okay? And you can really go in this other region, okay, where only repeaters can go. Sorry. So that's good. And so this means that, well, this orange region is actually accessible with an effective repeater, but you cannot go beyond that. And the question is how we can build, I mean, what are the repeaters that we can what are repeaters that the types of repeaters that allow you to go in this region, okay? Because you want to go into that region. You want to be the, I mean, you want to have a good rate somehow at longer distances, right? Okay, so in quantum distribution, there are three main ways to get into that region. Clearly, a very simple one is a trusted QKD node, okay? So in the middle, the third party is a trusted third party, okay? And that means that the middle part is getting the communication with Alice, the communication with Bob. The middle part is extracting two keys, one with Alice and one with Bob. And then, I mean, the middle part uses a one-time pad to combine those two keys into a single key, basically, which is shared by Alice and Bob. So that's a very simple process, very, very well known. It's still the node, which is in the middle, has to be equipped with quantum detection. Okay, so it is not a classical node because he has to get the quantum system from Alice, and he has to get the quantum system from Bob, or it has to send the quantum system to Bob. So he must have quantum hardware. Okay, it's not a classical node. It's still a quantum node. So it's somehow a quantum repeater in the information theoretic point of view. Then we have the untrusted node, so like MDI, so a measurement device independent, and the evolution of MDI, which is twin field. So this is the scenario here. So MDI is with the first two papers, and then the twin field, which is the very recent evolution. So what's happening is that Alice and Bob, they send systems to a middle repeater, so they can send, I don't know, coherent states or polarization states, and the middle repeater is doing a measurement. Maybe, for instance, in MDI, there's a bell detection. And then the outcomes are fed back okay, with a classical channel to Alice and Bob. Now, in this process, what's happening is that Alice and Bob, they are able to, a posteriori, I mean, after getting these outcomes, they are able to somehow have a correlated share randomness thanks to this process. And from this share randomness, they can extract the key. MDI is somehow, if you look at that, and also TF, they are somehow like they invert, I mean, the opposite situation of entanglement distribution, okay? So they're based on bell-like measurements. And you can see a bell measurement somehow as the opposite of sending an entangled state, okay, to remote users. In fact, I mean, MDI at the beginning was also, I mean, often, I mean, the first proofs of the MDI are based exactly on this idea of inverse EPR or inverse entangled state, okay? And then you have really entanglement distribution. Well, I mean, if your repeater is able to distill entanglements and distribute that, so you can go there, okay? Okay, so what's happening? And is that, okay, you have thin field that was discovered. So it's some thin field, it is MDI-like protocol. Very, I mean, an important breakthrough clearly in QKD. And you can see that it can beat the plot bound and can enter this region, okay? So that was remarkable. And after that, other protocols were designed. So these are actually some of the protocols that have been designed after twin field. And they're all somehow twin field nodes, twin field repeaters. So they can go here. So they're very advanced. And some of these clearly, I mean, have been also experimentally implemented. Okay, so that's good. So why I'm stressing a lot on twin field? Because it is basically a type of QKD repeater, QKD relay, which is able to go in this effective repeater region without using entanglement, and at the same time is a node which can be untrusted. So it's really, I mean, a remarkable combination of properties. Okay. Okay. So what's happening is when you take this into account. So we have these three types of repeaters that we can consider, three types of relays. And now we're using these three types of relays. You can think about three different types of QKD networks. Okay. So, I mean, the type of network, the type of architectures that you consider, basically, they depend on, clearly on these repeaters. Depending on what repeaters you use, you have an architecture of an app. So the simplest solution is clearly the trusted QKD network, okay? Where what's happening is that all the nodes are trusted, okay? Trusted means that, I mean, you are assuming that, well, a node in the network is not operated by the disruptor. So they're all authenticated and trusted users. So that's very, that is the situation. So you may have like a trusted LAN with users connected to a trusted hub, and another LAN, and then this trusted hub can be connected with another. So that trusted LAN can be connected with another LAN through a trusted repeater. Of course, we need this trusted repeater if this distance is somehow, I mean, larger than some amount. So you need these guys in the middle. Okay, so you cannot just have like direct communication. I mean, you can have direct communication, direct channel if you are short range. If you are already, I mean, at the size of, I don't know, like a small town. I mean, you really need, or I mean, a metropolis. I mean, if you are considering metropolitan network, for instance, then for sure you want to have these intermediate third parties. This is easy to scale because it's based on trusted nodes. It is point-to-point security, means that the security is between 2 points. Okay, so it's basically because the link basically is protected. So it's secure against attacks on the links, but clearly this requires that the hubs and repeaters are. Okay, it is a solution. It's a very near-term solution. This type of networks have been already implemented. They are very scalable. They have a level of security which is, in my opinion, acceptable. And I mean, this is an important technology which is still being developed. Then we have the next step. Okay, so let's try to remove some trust from the network. So we get you can use the second type of repeater now, which is the untrusted repeater. So I put this in gray to say that this can be untrusted, okay? And here you can use MDI or twin field, depending on the distance. Let's say use twin field, and well, you must still use trusted LAN, okay? And with trusted hub, but two LANs now are connected by this untrusted repeater. So now you have what we call LAN-to-LAN security. So if you collapse a LAN into a point, okay, you clearly have an end-to-end security from the point of view of the LAN, okay? So if the LAN becomes somehow, all these LAN become a point, a single node, you have a single node connected with another single node through an untrusted repeater. You are, okay, in a very robust situation. You are in a sort of end-to-end scenario. So in this situation, so the hubs are still trusted, the repeaters here are untrusted, yet not using entanglement. This is secure against attacks on each link, but also against the repeaters. So it's a kind of an intermediate step towards an high level of security. It is still near term. Clearly, there are experimental efforts in this point of view. I mean, people are implementing this. And so this is a really a viable solution, which is very good level of security. And yes, clearly near term. Then we have, okay, the third type of a repeater, we remember, which is the entanglement-based repeater. So if you really have that type of repeater with a reasonable performance, then you can connect different LANs, okay, using that repeater. In particular, you may use this kind of structure, clearly, which is pretty obvious. You may have like repeaters in the, okay, these entanglement-based repeaters in the middle, and then each LAN, so each local network is based on, well, basically an MDI, an MDI hub or a twin field hub. It's an MDI lab, which is an MDI hub, which is based on bad detection, for instance. That's a possibility. It's clear that it's working, and it's working in terms of end-to-end security, because the entanglement, which is distributed between, let's say, that hub and that hub, okay, there is entanglement between that hub and that hub. I mean, assuming that they can be synchronized with their measurement. So MDI, what does MDI? In this case, it does entanglement swapping. So on this MDI node, for instance, swap the entanglement and create entanglement between that hub and that hub. Now, this entanglement can be used and can be swapped to the remote users, for instance, and can be used to create a key. So this is clearly, somehow, well, from my point of view, is the most obvious structure, but it's clearly, I mean, it's the most this is the highest level. It's clearly not a near term, it's a longer term. You need quantum repeaters in the quantum optical sense, which are able to generate bright, well, it's able to generate a lot of entanglement pairs and so on. So that's clearly not a near term, but it's clearly where we're going at some point. Okay, so we are very last part of the talk. So whatever is your structure, what you want to have is about, okay, I can have like different types of repeaters at different times, near term, longer term. I can build the different architectures using these repeaters so that I can get into distance with some reasonable rate, perhaps comparable to what we have today in our classical infrastructure. Now, actually, we can also do something else. So in each of these architecture, we can optimize. We can optimize clearly with software. We can optimize with specific choices as well. For instance, the ideal structure may be a continuous variable, discrete variable structure. If you have a LAN, which is a short range in a building, you may want to use, for instance, continuous variable protocols because they may be very high rate protocols. And you may have very high rate communication within the users. Among the users within this network. Okay. And clearly, then you want to go out, but CV is pretty fragile at the moment. So what you can do for the repeaters, for the backbone, you can use the discrete variable. You can use discrete variable protocols. Okay, so perhaps you want to implement, I don't know, like here the VMDI and somehow Gaussian modulated protocols into the LANs. Clearly, you need also interfaces between these guys. Okay, but that would be a very important way to smart way to create high rate QKD networks. Clearly, there is also the problem of the routing, okay? So you may have like, when the scenario becomes more complicated, so you have a mesh network, if you're looking at a larger network with many nodes, many LANs, okay? You want to go from A to B, then at that point, in this kind of mesh network, clearly you have to consider optimization or the routing strategies. And this may be single path routing, so choosing like the best path each time, or maybe multi-path routing, and here you can have several possibilities. The most powerful thing you can do is flooding, where you're using all the network in parallel. And here, of course, I studied this situation a lot, and I also derived in the past information theoretic limits for these situations. Finally, very few words. These are the very last slides about satellites. So satellite can be now another element to be considered in optimizing networks. In particular, is a very important shortcut for global QKD networks. So if your local communities are very far apart, okay, so what you can do is using what you can do, you can use a satellite, clearly. And with that technology, really, you can connect this to communities, and the satellite can be of any type. It depends on how advanced it can be. As a relay repeater, it could be a trusted repeater, it might be an MDI repeater. It may receive an entanglement. So we already had experiments from this point of view. Also, even though with Michus, the rate was very, very low. But okay, you may have all of this, and these performances can all be improved. And regarding this situation, for instance, I also made a study in the past to see what was the performance when the satellite is just a trusted relay, a trusted repeater flying from one community to the other. Clearly, this is a satellite. It's very hard to be hacked from some point of view. So the trusted model is, in my opinion, quite appropriate, more than ground relays. So, consider a satellite as a trusted repeater, a trusted node is quite realistic. So in this study, what I considered, for instance, is to, flying a satellite from one station to another, belonging to different LANs. And this was like a sun synchronous at about, in the Leo region, about 500 kilometers. It was crossing the station. So, there are some parameters that I consider in this paper. I computed the composable finite size key rate that can be achieved in this kind of configuration. And I computed the number of secret bits per day that Alice in this station and Bob in this station can extract using that satellite. And then what I did, I compared that quantity given by the satellite with an ideal chain of repeaters. So let's say, okay, instead of using a satellite, let's put in the repeaters in the middle, a chain repeater, and compute the capacity of this chain. And so what I found clearly is that the satellite has a constant value. Okay, so it doesn't matter about the ground distance, no, because just flying from one side to the other side. So that is the good part of the satellite, that it is not affected by this decay. And you can see that, at some point, it beats the plot bound. So this distance here, about, this could be like 100 kilometers. And then it's able to beat one repeater, and then it's able to beat 5 repeaters, and so on. And well, this so you see that, I mean, at very large distances, over the 1,000 kilometers, that is clearly the best solution. Also because it's probably easier to, at the moment, probably, well, in terms of cost, to use a satellite instead of, no, 50 repeaters between two stations. So that is the beauty of the satellites. That is a credit shortcut. So it's able to somehow cut through these fundamental limits that you have on the ground, just because the thing is moving from one side to the other, and you are kind of collapsing this distance problem, okay, that is affecting the communication. So for large networks, this is certainly an important device to be considered, an important device to put in any optimization of large QKD networks. Right, so so this is the end. So take-home messages, and well, the first part, it was very general. I was just saying about, I'm just stating that, well, quantum safe communications are the building block for the quantum internet. We have many levels of security to consider. There is no optimal crypto system, okay, no ideal system in quantum safe communications. But we have to consider constraint optimization case by case. Why? Because there are many trade-offs. Okay, these trade-offs are about security, distance, rate, the number of users, and so on. The one very fundamental is between the rate and distance. There's the plot bound, and so we have seen the various types of repeaters can be used to bitless bound, and various types of QKD architectures that are based on these repeaters. Some of these are near term, others are, I mean, the last one was clearly long term. And finally, okay, whatever is your architecture, and so you want to optimize using, I mean, CB and DV in a clever way, optimize your routing strategies, and also potentially using devices like satellites if your network is very large. And yes, so that is all, and thank you for your attention.
Thanks, Stefano. Does anyone have any questions? Just jump in. Okay, so I have a couple. So you spoke basically a lot about QKD today, but in the first couple of slides, you did talk about further up the stack when we start talking about connecting quantum computers or having sort of like a true quantum network. Within the community that looks at repeaters and satellites, where do you think this is going to go? Because the trade-offs that you make in terms of range, speed, and fidelity for QKD can be mitigated using somewhat classical techniques, either privacy amplification and classical error correction, trusted nodes if you want the range to go further. And QKD doesn't require an overly high bit rate to actually be useful. But when it comes to like atmospheric attenuation or fiber attenuation, when we start thinking about a sort of true global internet or quantum internet, what advances do you see has to be made from the hardware side? I mean, do we simply need to come up with much better optic fibers with lower attenuation rates? Are satellites even feasible, given that we can't remove the atmosphere? I mean, what are your thoughts in regards to sort of the longer term future of quantum networking?
Yeah, I mean, the long-term future is about entanglement, right? Because I mean, it's the last type of quantum repeaters, these quantum optical repeaters, the one where you want the capability to distill entanglement and distribute that entanglement to parties, because that is actually the resources that you need for quantum computing. So you're right. I mean, that's different. I mean, the QKD doesn't need that. QKD only needs that at a very high level in device-independent QKD, but it doesn't need that for most of the applications, for the near-term applications. So from the point of view of the quantum distributed quantum computing, so the quantum cloud, so there is no way out. I mean, it's entanglement distribution, and you need to build very good quantum repeaters that are able to distribute entanglement at very good rates. And what you can have, certainly, at some point, suppose that you have this device that you are able to do the job. Well, you start to connect. You need to create a dense network on the ground. So probably centers where these quantum repeaters are not, I mean, more distant than 15 kilometers probably, or stuff like that. Because I mean, that's if you think in terms of, if I remember well, 15 kilometers was like the maximum you can get if you want 1 qubit per use of the channel, something like that. So you have like some kind of a range. Depends, of course, on the application, but you want to be dense. So you want to create centers where, probably in cities, where basically you have these quantum repeaters that can create bright entanglement and distribute that to the centers. Clearly, if you work with the connectivity, then you enlarge this network and you somehow overcome the problem of the distance and so on. So it is going to be, in my opinion, in particular, a very local, regional effort. Clearly, there are projects that are building want to build quantum repeaters who connect very distant locations. I don't know, like Tucson and Boston, or other in Europe and so on. And clearly, that's possible as well, not because you can do that. These types of repeaters, in my opinion, represent well, important advance, important test bed. But at those distances, clearly, you cannot have a really, I mean, high performance, an high performance quantum computing situation. I mean, this is more about for proving that you can do that at a large distance. You may do for ultra secret communication if you want. But the point is that I mean, you really need to connect something like a Boston Tucson on the ground. You don't need a repeater. You need many repeaters in the middle. Okay? So you need to build a chain. Or you need to, I mean, and clearly when you start building the chain, then you start building also the network, and you can use multipath routing in the network, considering that entanglement behaves differently from classical information. So you must be careful when you do the multipath routing that you can, how to do that. And so clearly at that point you can increase. So in my opinion, I mean, the first effort for these distances are very low rates, but then you can start to see important advances where you have repeaters which are not so far one from the others, and you are in a situation where the connectivity of the network is non-trivial. So it should be like a local area within a city. I don't know, be like the size of, I don't know, Palo Alto, for instance, or something like that. Yeah, I don't know if I mean, did answer your question.
Yeah, it does. I was just also wondering, I mean, is there anything about what you're developing with nodeQ that you're able to talk about or willing to talk about? I'm interested in what your startup is intending to produce.
Yes, okay, thanks for the question. So first, the startup is really based on my expertise and other people which are involved. And so we're looking at networks and quantum networks. I'd say networks, also classical networks, besides quantum networks. And the company is about software development. Well, at the moment, and we are looking at the problem of designing, optimizing quantum networks, and also somehow controlling quantum networks in somehow so to give the best performance in real time, and so to achieve somehow the best working point. We are looking at security, but also the other steps of quantum computing. Clearly, security is really the most urgent. And when I say security, I'm not just talking about quantum key distribution, but also post-quantum crypto. I mean, if you say post-quantum crypto is most likely a very good compromise to be implemented in the US probably soon, and well, it's very slow, okay? And yeah, take a crypto system like a McAllis, and it works with 1 megabyte of key size instead of 2K as RSA. So you have stuff like that. So you have a huge slowdown of performances, even if you come up with a post-quantum crypto network. So so that's also what my company is doing. So it's optimizing this type of networks as well, but also looking at the next step of QKD. Well, next step, not really next step, because QKD is coming together with post-quantum, especially in Europe and other places. And so it's specifically looking at optimizing the performances of these networks that will be very slow without a brain which is orchestrating all the devices, the parameters, the systems, the routing, and so on. And the same is valid for the next steps for distributed quantum computing, so for a quantum network. You know that the most promising device is at the moment, well, one of the most promising is superconducting quantum computer. Well, good. Try to connect two of them through a fiber, which is now the most important and important link. Well, you need interfaces. Now, these transducers between the macro and optical. And of course, this exists. You have these transducers, but they are classical. They are developing the quantum version of them. They're improving the performance. When you transduce a photon from microwave to optical, you want to keep also the exotic quantum features like superposition and entanglement. And that is very important. So, and there's an efficiency from that point of view. There's an efficiency in terms of how, for instance, how much these features are maintained. And so it's very important to understand, for instance, this kind of interfaces. So a network, a quantum network like that, involves interfaces, involve the complete quantum computing devices, involve optical switches, a lot of elements, and all this must be coordinated. And I guess also Simon, you are also an expert in this, right? In this
well, not in recent years. I haven't looked at comms for a while.
Yeah, okay. But I know that you have also studied quantum networks. So this it's a very complex scenario, and it really requires what I would call a brain on top of that. So that's why we're doing. So trying to develop this brain using my brain and brain of other people like also Sam Brownstein and other people. Yeah.
Cool.
Yeah.
Okay. Well, thank you again, Stefano, for staying up late, and thanks for everyone else for getting up at a reasonable time this morning. Other than that, I'd like to give Stefano a very hearty virtual clap. So thanks again.
Thank you very much.
Thank you.
Yeah.
And thanks, Stefano. We'll obviously, this talk will be up on our YouTube channel, and we'll be hosting the audio on the podcast as well fairly soon, where you'll get the vast majority of your audience.
Okay, thank you very much, Simon. I really appreciate it. And also,
thank you.
To say bye to Zishina this day, I can see that.
Thanks a lot, Stefano. Have a good night.
Bye. Bye-bye to everyone. Bye.
Catch you.